All right, thanks a lot for the introduction, and thanks for inviting me here and welcoming me to give a talk to LIDS. This is my first LIDS conference. Certainly heard of it before, and the many renowned people who have participated in LIDS over many years. Today I'm going to tell you about very recent results that we haven't even published them. And when I was invited to give this lecture, I thought it would be of interest, and then I looked into your profiles and I realized this is precisely the kind of topic that you're working on, and it's relevant, and so I thought that was really nice. Well, I guess one thing I'll say about myself, you were talking about my background. So in quantum information, it's a very interdisciplinary field, right? And so my undergrad was computer engineering, then I did my master's and PhD in electrical engineering. I did a postdoc in the School of Computer Science at McGill, and then I was a professor for a decade at Louisiana State University in physics, right? And now I've come full circle back to EC at Cornell. And it's very exciting in this field to have learned about so many different areas, how quantum intersects. Like there's this keyword quantum, and then it can intersect with many different fields in non-trivial ways. And so that's been particularly exciting, and it's something about the field. That maybe that will change as the field gets larger and larger and people get more specialized, but at least, you know, I was able to take advantage of that. Okay, so this work is about a particular class of channels called bosonic dephasing channels, and one of my goals is to unwrap what this means for you. Also, since this is a relatively small group, I encourage you to speak up, and I don't care if it's being recorded. Maybe I'll regret saying that later. But feel free to speak up and ask questions, and I can go to the board and clarify points. It doesn't really matter so much if we get through all the slides. I think it will actually be impossible considering the slides that I made. So this is joint work with my colleagues Zishin and Ludovico. Ludovico I've worked with for maybe almost the past decade. I'll actually visit him after this in Amsterdam for 2 weeks, and Zishin I started working with more recently. Okay, so what is our goal today? Dephasing is a prominent noise mechanism that occurs in quantum systems, and it presents a challenge to useful communication, computing, and sensing. And the class of channels called bosonic dephasing channels, these model noise in fiber optic channels or superconducting circuits. Here at MIT, I think you have people trying to build superconducting quantum computers, so this presents an obstacle to doing so. Even in ion traps, you'll also find this dephasing noise mechanism. Okay, and the goal of today is to understand how well can we discriminate two different kinds of bosonic dephasing channels. How well can we estimate parameters encoded into bosonic dephasing channels? The main example we'll study is like the variance of the noise. If you want to estimate the variance of the noise, how well can you do so? Okay, and so and also communication. So fundamentally, these are information and decision problems, right? So you should be very interested in this in principle. Okay, so I'm going to start and give you, basic backgrounds on quantum optics, the basic background that you'll need to understand what I'm talking about. And I think the math is fairly simple. There are equations on the slides, and so, but as you know, my goal is to express the ideas effectively, and I have various figures that I made to help explain that. So let's start with quantum optics, crash course. Okay, first thing, what is a quantum state of light? You can have a state of light that has no photons, that's called vacuum. you can have a state of light that's 1 photon, 2 photons, etc. But in quantum mechanics, you can also have superpositions of photon number states, right? So it can somehow simultaneously be 0 photon, 1 photon, 2 photon at the same time, right? And there are various interpretations associated with quantum mechanics. I'm not going to get into that today, but that's a whole area of research that you can study called quantum foundations. Okay, and you can have 0, 1, 2, and there's a countable number of photon number states. Okay, and we do use this notation from Dirac. That is somehow unavoidable. But what this means is it's a label for a vector, right? So if I were to write, the vacuum you can think of as a vector with 1 followed by an infinite number of zeros, so an infinite dimensional column vector. 1 would be the ones in the second spot, and then an infinite number of zeros. 2 would be this, etc. Right? At least mathematically, that's how it's represented. Okay, and so a general quantum state, often denoted by psi, can be a superposition of these photon number states. And Cn is a complex number. Every Cn is a complex number. And the only constraint on them is that the sum of their squares is equal to 1. Okay? This is what's called the Born rule of quantum mechanics. There's an interesting story to tell about the Born rule. In Max Born's original paper, before it was published, he didn't put the square, right? And then before it was, in the final proof, he somehow, this is what I heard from others, I don't really know, but somehow he realized the square should be there, that was fundamental, and he put it, and that's what he won the Nobel Prize for. So, this Born rule of quantum mechanics, this fundamental notion. So this is there, this corresponds to the probabilistic interpretation of quantum mechanics, okay? So if you were to prepare a mode of light in this superposition photon number state, and you were subsequently to do a measurement, which corresponds to asking, like, okay, how many photons are in the state, then you get a probabilistic outcome, right? So with the probability Cn squared, you get the number n, that there were n photons, okay? And here I'm using the Dirac notation that indicates an inner product between this distinct photon number state and the original state, okay? Good. So I guess it was clear from what I said here that the photon number states form an orthonormal basis, but let me emphasize that again, right? So this forms an orthonormal basis, and that will be an important concept throughout the talk. Okay. Continuing with the crash course, there's an observable that corresponds to something you can observe, and in this case it's photon number. That's described by a Hermitian matrix, okay? So the relevant observable force is denoted by this. It's common to put a hat on an observable. And this Hermitian matrix, its eigenbasis is the photon number basis, and the eigenvalues correspond to the number of photons, okay? And this notation, this is like a column vector, this is a row vector, and so it makes a projection matrix onto the nth photon number, okay? And if you want to know the expected value of the photon number of a given state, then there are various ways of writing this mathematically that are equivalent, okay? This is the way you would write it if you're coming from probability theory, right? It's like the inner product between the probability distribution and the photon number. That's the expected value. If we substitute what we had for the probability mass function, then it would be these Cn coefficients. You can work through some math and see that these two expressions are equivalent to this expression, the second one here. And that's also the same as using the photon number observable and using the trace overlap of the matrices. Okay, so those are all calculations you can do. And these can be understood as different ways of representing the Born rule also. Okay, good. So those are some basics. I'm curious, who here has taken quantum mechanics before? Please raise your hand. Okay. So this is maybe familiar language to some of you or an introduction for others. Okay, so I said that the talk was about dephasing, right? So to understand that, we need to understand what is the phase operator. So how can the phase of a state be changed, right? So mathematically, that corresponds to this. And if you've studied quantum mechanics before, if you exponentiate a Hermitian operator, which corresponds to a Hamiltonian, that is the solution to the standard Schrodinger equation of quantum mechanics. And if you exponentiate a Hermitian operator like this, then you get a unitary operator, okay? And so, the basic evolutions of a state in quantum mechanics are described by unitary matrices. Okay, so that's what I've done here. I put the photon number observable, and I'm picking the phase parameter, phi. It's going to be a phase, so it's a number between minus pi and pi. And if you work through the math, basically what you do to get from this expression to this one is, on the previous slide, we had the, this representation of the photon number. If you're evaluating a function of a Hermitian matrix, you evaluate the function on all the eigenvalues, and that's like the standard functional calculus way of evaluating a function of a matrix. Okay, and so that's what we do here. And then it's an interesting calculation to take the state I had in the previous slide, which was a superposition of photon number states, apply a phase rotation. And then when you do so, using the orthonormality of the photon number basis, then what you find is that these are called relative phases. They get introduced on every photon number state in the superposition. Okay? So that's what a phase rotation does to a quantum state. And this is a deterministic phase rotation. Every unitary matrix can be inverted, right? And so if you knew what the phase was, you could invert this operation and recover the state perfectly, okay? The case we'll be interested in later is when you don't know the phase, what kinds of statements can you make in information and discrimination and decisions, right? Okay, and this is kind of a picture meant to illustrate what happens with a phase rotation in like a cartoon way. So if you prepare a mode of light in a certain state before transmitting over a cable, it goes the path length that it's traversing induces a phase, right? And for various reasons, temperature fluctuations, unknown uncertainties in the path length, you might be uncertain which particular phase has been applied, right? And so that will correspond to this noisy bosonic dephasing channel that we'll get to later. Okay, the first thing I want to talk about is, suppose it's your goal to estimate an unknown phase. What can you do, right? What kind of strategy would you employ? And this is something that's been studied a lot by physicists. When we were working on this paper, we just quickly came up with these two schemes that I'm going to present to you, and then we kind of knew that we would have to do literature searches to find all the different papers where people have studied this. So last week I was visiting University of New Mexico, and I talked to an experimentalist, a quantum optics experimentalist, and I was very happy that he pointed me to the various papers. What's interesting for electrical engineering is that you'll see familiar expressions when we go through these methods for phase estimation. Like you'll recognize a sinc function, so maybe you'll be happy when you see that. Okay, so what is the first method? We're going to suppose that a phase operator is being applied with some deterministic phase parameter between minus pi and pi, and your goal is to figure it out. So you don't know what it is beforehand, but your goal is to figure it out. So what can you do? Well, this is one strategy. You can prepare a uniform superposition of all photon number states going from 0 to d minus 1, okay? And has anyone studied quantum computing before? Okay. So there's a famous algorithm called the phase estimation algorithm. And what I'm showing you here is kind of like a quantum optics version of that. Okay? And so this first step is essentially identical to the quantum phase estimation algorithm, which is kind of the workhorse behind many algorithms that lead to speed up over classical computation. Okay? Here we're not necessarily looking for a speed up. We're just trying to understand methods for estimating an unknown phase. Okay, so first we prepare this uniform superposition state. Then the phase operator, the unitary phase operator gets applied. And using what we had in the previous slide, then this phase gets encoded in this state as relative phases. Okay? So what should we do from here? Any thoughts? Based on what you might know from signal processing? Fourier transform, beautiful. So that's exactly the right idea. Fourier transform, and this will be a discrete Fourier transform, that's a unitary operator. And so in principle, it has an implementation in a quantum optics lab, although that's quite challenging to do. And so people are actually thinking about, well, maybe you should first convert this to qubit states and then just do that on a quantum computer, okay? But in principle, any unitary evolution is allowed by quantum mechanics, but that's a different story to figure out how to implement it. But that's a great idea, and that will do the job. Okay, so if we have the Fourier basis, that corresponds to a measurement that we can do, okay? I guess I didn't have a slide on measurement, but let me write that briefly, what happens. So if a state psi is prepared, and you have an orthonormal basis, I'll call it phi k, right? And let's just suppose it's finite dimensional for simplicity. Then if you measure in this basis with probability p of k equal to the overlap with psi, you'll get the outcome k, right? So I guess I illustrated in the first slide that this is the kind of thing that would happen for a photon number measurement, but now this is like the general rule. So this is the general rule of the Born rule of quantum mechanics. There are all these Born movies, Born, what were they? Born Supremacy, Born, thank you, Born Ultimatum. There was a third one. Sadly, there was never a Born rule. That would have made quantum physicists really happy. But quantum has seeped into some Hollywood movies like Ant-Man. I actually have a funny story about that I'll tell briefly. So I was back home in Louisiana doing a workout, and there was a young girl, and she was 10, and I was doing some exercises, and she said, "You look like Ant-Man. Are you Ant-Man?" And I said, "Do you think I look like Paul Rudd?" "I don't think so. He has a lot more hair than I do." And then she said, "Well, what do you do for a living?" And I said, "Well, I do work on quantum mechanics." And she said, "You're Ant-Man, without a doubt." Anyway, so I'll never forget that because it was so funny. And her boldness, as a 10-year-old girl talking to me like that. Anyway, so back to the story. We're going to do a Fourier basis measurement. And then when you do the calculation, this is kind of like a standard calculation you do in signal processing class in electrical engineering, but now using this funny Dirac notation. And what you end up with for the probability distribution of observing outcome K is essentially like a sinc function, right? And it's peaked at phi equals 2 pi k over d, right? So if you take the limit as d gets large, then this value 2 pi k over d will converge to the true value, okay? So this is an important observation for later on. Our work is about determining the fundamental limits of discrimination and estimation of bosonic dephasing channels. And as part of this effort of determining the fundamental limits, we're not making any energy constraints, okay? And so we're going to allow ourselves to take this kind of limit. Part of the future work which we're actively thinking about is what are the limits when there are energy constraints in place. But prior to our work, we're not aware of anyone even determining the fundamental limits that are allowed in the physical universe. Okay, so this is one method for determining an unknown phase. There's another method that's very interesting and much simpler to implement from a technological perspective, right? We were just saying that you might need like a quantum computer to implement this kind of measurement. And so there's a question of, well, what are the other schemes that are simpler? Okay. Sorry, this is a summary. This is like a diagrammatic summary of the method. So first we prepared the uniform superposition state. Then the unknown phase operator gets applied. Then you do a measurement, gets an outcome k. You change that to 2 pi k over d. And then the limit as d gets large, this converges to the true value. Okay. What is method 2? This is easier to implement from a technological perspective. There are states of the light field called coherent states. They were theoretically described by Roy Glauber, who I think was a Harvard professor. Am I right about this? Yes, thank you. And he won the Nobel Prize for his work. Have you read his paper?
Yeah, Glauber.
Roy Glauber, yeah. Do you remember the year it was written? Was it like 62 or something?
63 or something.
Yeah, so a long time ago. And was very foundational for the field of quantum optics. And when I was learning things, I actually did read his paper. It's very beautifully written, so I recommend doing so. Although you can find these in many textbooks. So what are these states? These are particular superpositions of photon number states. And they are characterized by a complex number alpha. Okay, so you write them like this. One thing to remember with this Dirac notation is kind of the rule that anything can go in a ket. So this thing is called a ket with the vertical bar and the angle bracket. And when you start reading physics papers, you'll see all kinds of funny things in kets, like cats, dead cats, alive cats. I've even sat in talks where people will put like artistic diagrams in a ket and it means something. But when you see alpha in a ket, sort of undoubtedly, it's a coherent state. So it's something you just have to know. And it's this sort of, these are the terms in the superposition. And this is a normalization factor. Okay? And what's nice about this is if you read quantum optics books, they'll talk about phase space. It's a way to visualize states of the light field like they're in the complex plane, okay? So, you know, if alpha is a complex number, this will be the real part of alpha, imaginary part. And suppose it's some complex number here. When it becomes a quantum state, due to the uncertainty principle, the way we visualize it is like a ball of radius 1 or 1/2. It depends on various conventions. It depends on maybe how you set h bar. So in quantum mechanics, you can try to measure the position quadrature or momentum quadrature of a light field, of a mode of light, and you'll get a random outcome. And the uncertainty principle tells you that the product of the variances has to be greater than 1. Okay, again, that depends on how you set h bar. And so this is meant to represent that uncertainty ball. Okay? You know, the vacuum state would be down here with the uncertainty ball of radius 1. And all coherent states can be realized by displacing the vacuum. And that corresponds to a unitary physical operation that can be realized in the lab, or at least approximated. Okay, so the idea behind this scheme is to prepare a coherent state, and we'll just take alpha to be real, right? And then one thing that's very beautiful when you work through the math of the phase operator is that the phase that's here gets applied to the complex number alpha, right? So if we start with a real number, the phase will just take you around in phase space, around the unit circle, right? And this uncertainty ball moves along with it. Okay, so that's a very basic idea. And also, these coherent states are what's called Gaussian states. And what I read is that, and what I hear all the time, is that they're very easy to prepare in the laboratory. And that's very commonly done here and other places. Okay, so then we're trying to figure out what that phase is, right? Like, if the phase gets applied, it'll, you know, if this is like the angle phi, then we'll end up over here, right? And then we want to measure and try to figure out what the phase is. So there's a measurement you can do, and it's called heterodyne detection. And it corresponds to this mathematically. So it's like a projection onto the coherent state basis. But these coherent states are non-orthogonal, and they form an over-complete basis. Okay, and this 1 over pi is a normalization factor. So when you do heterodyne detection, you'll get a complex number that we'll call beta. Okay? And, you know, we want beta to correspond to alpha e to the minus I phi, and then we can compute the angle of beta and get an estimate for phi. Okay, so that's a very basic idea for phase estimation. And you know, it's much easier to implement in the lab. And we were working on this recently, and I was very pleased to, you know, you mentioned that I did my PhD at USC, and we were talking about quantum control. We were talking about, sorry, I mistakenly put quantum in front of everything sometimes. We were talking about control people, and I was very pleased to find this paper of Edmond Jonqueret at USC with some colleagues of his who worked out what is the probability density of observing the phase. They were looking at complex Gaussian random variables, but it applied directly to the situation in quantum optics with coherent states and heterodyne detection, because through this scheme you will get a Gaussian probability distribution for a complex number. And then if you try to calculate that phase, that's what they call the Ricean phase distribution. Okay, so they worked out the mathematics of it, and they found this somewhat complex expression with the main property that as alpha becomes large, this converges to a Dirac delta, right, around the true value, right? So this, you know, as alpha gets large, this will converge to a Dirac delta phi hat minus phi. So you're getting like a very precise estimate of the phase, right? And so like the way you can think about this intuitively is if alpha is getting larger, this uncertainty ball is so small in comparison to a very large alpha that you'll be able to get a very fine estimate of the phase in the limit as alpha gets large. Okay, and again we said that for the purpose of determining fundamental limits, we're not concerned with energy constraints, so we're allowing that kind of thing. Okay. So those are some ideas. I have until 3, right? Oh, 3:05. Negotiate a little more time. So we're roughly halfway through. And again, if there's any questions, feel free to speak up or ask at any point. Because we're about to continue to new territory. Okay. Good. So, yes, this is a summary of the scheme that I just talked about. We'll call it the coherent state method. You prepare the mode of light in the coherent state alpha, where alpha is real. The unknown phase gets applied. You do heterodyne. That gives you a complex number. You compute the angle, and then this becomes a highly accurate estimate of the unknown phase in the large energy limit. Okay. What is the bosonic dephasing channel? So this is going to introduce probabilistic notions. Right? We've already had probability there from quantum mechanics and the Born rule. We've been talking about that. But this can be considered kind of like a classical probability, like an uncertainty about an unknown phase. Okay? So now we're going to suppose that a phase is chosen at random according to some underlying probability density, right? That's on the interval from minus pi to pi. Worst case scenario, that's uniform, right? Better is if it's what's called wrapped normal distribution, like it's becoming closer to a Dirac delta. Okay. So this phase is randomly selected, and this way of thinking is actually going to be very helpful, what I'm talking about now, for figuring out the fundamental limits of the bosonic dephasing channel, like breaking its action into a sequence of steps. So an unknown phase is chosen according to a probability density, and then depending on the value that's chosen, a unitary phase rotation gets applied. Okay? And the result is a probabilistic ensemble. Right? So with probability density p phi, the state is the phase rotated state according to the phase phi, right? And then, this is some number between minus pi and pi. So far, when we talked about quantum mechanics and states, we used what's called the state vector formalism, okay? There's an alternative formalism which was developed by von Neumann in the very earlier days of quantum mechanics called the density operator formalism. And what you do is, to figure out the density operator corresponding to a probabilistic ensemble, you take each state in the ensemble and form its column vector and row vector, so it becomes a matrix, right? And then you average over all the states in the ensemble. And this right here is a matrix, okay? And in principle, it could be an infinite dimensional matrix when we're talking about bosonic modes. Okay, so the way you should think about this is that a receiver who's trying to figure out what the unknown phase is, or maybe estimate something about this distribution or discriminate it, one distribution from another, you should think that the receiver gets a state that's described by this density operator, okay? And so then we have to, start thinking about the mathematics a bit of this kind of density operator. Okay, I do have a little quantum mechanics further crash course just to let you know about density operators. So if we have an orthonormal basis, we can expand any matrix with respect to that basis, right? So photon number basis is an orthonormal basis, and we can expand an arbitrary density operator with respect to that basis like this. And so these rho and m, these are the matrix elements of the density matrix, okay? And what are its constraints? The constraints are there to be consistent with the probabilistic interpretation of quantum mechanics. So these matrix elements should form a positive semi-definite matrix with trace equal to 1. So what does that mean? The eigenvalues of the state are a list of numbers that are non-negative and sum to 1. They correspond to probabilities, right? These constraints ensure that any measurement that's performed on the state results in a probability distribution. Okay, so everything's consistent with this probabilistic interpretation of quantum mechanics. Okay. And to revisit some things that we talked about earlier, a photon number measurement on this state, it'll give the outcome n with this probability. You form these projectors for the photon number states and overlap them with the state of interest and compute the trace. And that gives you the probability of observing outcome n when you do a photon number measurement on a state described by this density matrix. And the expression for the expected value becomes more compact. You can write it as this trace overlap. Okay. And, okay, one more thing. The effect of a phase rotation on a density operator, it's this. And that's consistent with the expression we had on the previous slide for how we would get the bosonic dephasing channel acting on a pure input state. Okay, so all of this together, this leads to the most general way that we can write the bosonic dephasing channel. There's an underlying probability density. That's this P of phi, and then the phase gets selected, a unitary rotation is applied. Since we don't know which one was applied, we describe the resulting density matrix by this, okay? There are some senses in which this is analogous to like marginalizing over a probability distribution. Like if you have some uncertainty about something, you marginalize over the variables that you don't have access to. Okay, so this is the object we'll be thinking about. And now I want to move on to the actual task. We did talk about methods for phase estimation, and that will come up. But now I want to apply them to a particular task called channel discrimination. And this is where you're trying to decide, am I seeing one bosonic dephasing channel or another one, right? So that would help you to judge like the noise on a fiber, right? Or the noise in a quantum computer. It's like the very basic two hypothesis distinguishing like decision task. Okay, so this is where we have some figures to help visualize what a quantum channel discrimination protocol looks like. And we're going to do it in the general sense first, and then we'll start applying it to bosonic dephasing channel. Okay, so we're going to suppose that there's two quantum channels, two quantum noise processes that we're trying to distinguish. And we're going to be allowed to call the unknown channel little n times. Okay, and then we want to know things like the error probability in making a decision as a function of the channels, right? So if they're less distinguishable, we'll make a higher error. If they're more distinguishable, we'll make a smaller error and decide in between them. Okay, so this is what a protocol for quantum channel discrimination looks like. There's an input state that I'll call tau. So we'll suppose that in the background, I, the choice of channel, is selected. Right, we're trying to figure out I. So I is chosen, and the first thing we're allowed to do is to input one share of a correlated state. And this is the most general thing you could do in quantum mechanics, by the way, right? So this state right here could be what's called an entangled state. I haven't talked about that yet, but that's an important concept in quantum information. So I'll give you an example of an entangled state. If we take those Cn coefficients and put them in the superposition, and instead take the tensor product of the photon number basis states, this is what's called a two-mode state. So you can think of it as like one mode of light is here with, say, Alice, and another mode of light is over over here with Bob, right? And then they can use this to their advantage in a variety of quantum information protocols, one of which is channel discrimination. So there could be a benefit to using an entangled state versus an unentangled state, okay, when you're trying to make a decision. So this is like a very basic form. As long as two or more of these CN coefficients are different from 0, then the state is entangled, okay? And entanglement's responsible for a lot of the funny effects that occur in quantum mechanics. But I'm actually not really going to get into that today. We're going to reduce all of this to a classical decision problem. That's what's going to happen, which is somehow really satisfying. So in the paper, there's no quantum formulas, right, except for like the Born rule. Most papers that I write, I introduce like 3 versions of quantum Renyi relative entropy, or like 2 versions of quantum relative entropy, or 2 versions of quantum Fisher information. But with this work, there's no need for any of that. Everything just reduces to classical, where there's like a unique formula for each task. So that's something that was nice. Okay, so a channel discrimination protocol begins with a state tau, and then you call the channel once. You input 1 share of the state tau to the channel, and then there's an output. And then you're allowed to apply an operation to help you make a decision at the end, right? So this itself could be a measurement. It could be a unitary evolution. It could most generally be described as a channel itself. Everything in red is parameter independent. Everything in green is parameter dependent. Okay, so this color coding will be useful for our reasoning later. After this first call, first adaptive operation, you're then allowed to call the channel again, a second time, right? And then you feed something in, and then something comes out. You're allowed to call another adaptive operation, call the channel again. This is where little n equals 3. You're calling the channel 3 times. And then at the end, you're allowed to perform a quantum measurement, which has a classical output, which is binary, and that's your decision, right? So that's your decision. And yeah, so a particular strategy for channel discrimination consists of tau, the 2 adaptive operations, and the measurement. And in general, if there are little n uses of the channel, there will be n-1 adaptive operations. Okay. We're going to denote the final state of the protocol by rho I, because it depends on the channel I that was selected. And there'll be an n there because we called the channel n times. Okay, so the final state will denote by rho I n when channel ni is selected. The final measurement we're denoting by this curly q, which is a binary measurement that has 2 outcomes, right? I equals 0 or I equals 1. We're trying to figure out which one it is. And the constraints on these measurement operators are constraints from quantum mechanics. They have to be positive semi-definite, and they have to sum to the identity. And those constraints are there, and they're consistent with, observing probability distributions after doing the measurement. Okay. So in this task, there are 2 kinds of errors that can occur. Type 1, type 2, or the more boring names from statistics. In radar theory, you call them false alarm and misdetection. So, if 0 is the null hypothesis, for example, in radar, if nothing's there, then this is the probability of a false alarm, saying that something's there when it's not, right? And just in mathematical terms, it's when I equals 0, but you declare I equals 1, so you made an error, right? And from the Born rule, this is the probability of making that type 1 error. Okay? Yeah?
Is the reason you're using binary measurements because that's the optimal thing to do?
We're saying you have to make a decision. Yeah, we're not allowing I don't know. Okay. Yeah, but that would be a different scenario. And yeah, I think we could add that to our paper. Like all the results that we have, like reduction of quantum to classical would still apply for that scenario. But that's a good point. Yeah. Okay, and this is the probability of making a type 2 error, right? Misdetection. Something was there, but you didn't detect it. So it's just, everything's flipped, right? So this is the final state at the end, and the probability that you declare I equals 0. So those are the two error probabilities, and these are the things we want to analyze. And what I want to prove to you is that in the roughly 10 or so minutes remaining, that functions of these error probabilities, like optimized functions, will reduce to kind of the same functions, but for the classical probability densities underlying the channel. Okay, so that's the main point I want to get to, and then there's probably all kinds of other stuff that we won't get to, and that's totally fine. Okay, so let's start with the symmetric error setting, also known as the Bayesian error setting, right? So there's a prior probability that channel 0 is selected, and that'll be lambda, and with probability 1 minus lambda, channel 1 is selected. Okay? So the minimum error probability is just this. You take the average of the two errors according to this prior, and then you minimize over all possible adaptive strategies allowed by quantum mechanics. Right? Okay, so that's what we want to study and understand. And what I want to prove to you is that this will reduce to a classical hypothesis testing problem. Okay? And I just want to give you the idea of why that occurs. And that can be accomplished with the methods that we talked about earlier, as well as some visualization diagrams. Okay, so in classical hypothesis testing, you can suppose that you're given n samples from a probability density, right? So maybe the two situations are P0 for the first bosonic dephasing channel. Oops, I should make this minus pi to pi. Maybe it's skewed like this, right? This would be P0. And P1, maybe it's skewed like this, right? But in the quantum problem, you don't observe this. You don't observe samples from this. This gets filtered through the phase unitary operator that gets applied, right? So there's an extra quantum noise that occurs. Okay. But if you're dealing with an entirely classical problem, and this is the density that you're sampling from, and say you get n samples, you would expect most of the samples to occur in this range where there's higher probability, right? And so, if that's happening, you would have some simple decision rule to separate you from, sorry, I should have written P1 here. The other hypothesis, P1, okay? And in this scenario, most of the samples will be coming from the right side. So that would be some kind of basic decision rule for this scenario. In this classical hypothesis testing problem, these are the expressions for the type 1 and type 2 error probability, right? You're allowed to do some randomized tests when making a decision. So that's described by this T here, which will be a randomized test. Okay. And the expression for the minimal error probability in the classical setting is this. You take these type 1 and type 2 error probabilities and minimize over all possible classical tests. Okay? And so that's a well-known expression that has been studied for a long time. Okay. The main theorem is this. If you're dealing with bosonic dephasing channels, the quantum expression is equal to the classical expression. Okay? So, and the goal of the rest of the talk is to convince you why that's the case, right? And again, in this scenario, we're not assuming there's any energy constraint, right? So the attainability part of the proof, we're just going to use one of those two methods from before, which allowed you in the infinite energy limit to like deterministically get phi, right? So when you're using those schemes, it's like you're obtaining samples from the underlying probability density described in the bosonic dephasing channel. So that's what it boils down to for the attainability part. Okay, and so this is what I was just saying. Like, use one of the two methods we talked about previously, but now there's a, the box, which previously had the unitary phase operator, is replaced by the bosonic dephasing channel, which has this like extra classical uncertainty to it. So method one, you do the photon number superposition preparation, the channel gets applied, you do the Fourier basis measurement, get an outcome, and the limit as d goes to infinity, as the energy is going to infinity, it's like you're obtaining a sample from the underlying probability density. So that's the main idea for the attainability part. And you can use the second method also. And it's a very interesting question how these compare in the finite energy case. That we haven't done yet, but the math is there to do it. Okay, and then, what I said we wanted to prove was an equality between the quantum expression and the classical expression. Because this is an achievability scheme, this is one kind of scheme that you can use, right? You can use method one or method two, effectively obtain samples from the underlying probability density and apply any classical test to those samples. And so, the minimum error that you can achieve using this approach is an upper bounds on the minimum error allowed by all possible strategies in quantum mechanics. This is like a particular strategy that we're using, and but it's not all possible strategies. But what we can show is that you can't do any better. It ain't any better, right? So what is the key idea for optimality? This is the idea of simulation. And the reasoning behind this actually just follows the description of the channel that I gave you, these 3 steps, right? So the dephasing channel can be simulated by a 3-step process. The first of which is parameter dependent, and the others are parameter independent, okay? So the first part is that the parameter dependent part. It depends on the underlying density, right? So you can think of there's this environment picking a phase according to this underlying density P of phi, right? And then the channel then applies this phase rotation. So the way that I wrote this here, it might look that it's parameter dependent, but it's actually parameter independent, okay? And I'm going to describe more why that is on the next slide. But I think if you've studied quantum mechanics, quantum computing, we can describe this second step also by like a controlled unitary, okay? And I'm going to use phi prime to indicate that it's like a dummy variable that doesn't depend on the parameter. So like controlled on the classical value that's chosen in the first part, you then apply this phase operator, e to the minus I n phi prime, to the input. And then you discard this first register. So this is the step that's parameter independent. And that's the key insight for this channel simulation, and which we'll use for optimality. Okay. So mathematically, the simulation of the channel we can write formally as I've collapsed it to a 2-step process. The first of which is parameter dependent. It depends on the underlying density of the channel. And the second part is kind of like this controlled unitary and discarding this first register that has the value of the phase encoded in it. Okay, and so that second part is parameter independent. This is the formal thing. I'm basically out of time, so what I want to do is argue the rest of it through the diagrams. Okay. So what we're going to do with the diagrams, and considering a general protocol for channel discrimination, I'm going to substitute every call to the unknown channel with its simulation, right? And you see this part is parameter dependent, but then this part is parameter independent, okay? So this color code will be helpful for visualizing everything. Okay, so this is what a general protocol for channel discrimination looks like. We then substitute every call to the bosonic dephasing channel with its simulation, right? And then these are states that are encoding like the selection of the classical value of the parameter according to the underlying probability density. And because they're states in the simulation, I can pull them back in time, right? And I can imagine that they're prepared earlier, and then at the appropriate time, they're interacted with the input state to the channel, okay? So that's what we're going to do now. And so then what we see is that a general channel discrimination protocol involving the bosonic dephasing channel, when we substitute this simulation, we can view the whole thing. It has, these are actually classical inputs that are selecting the samples from the underlying probability densities. And this is the measurement which produces a classical output. So the whole protocol is just a classical statistical test on the underlying samples, right? And so this is possible for any channel discrimination protocol, right? We can view any channel discrimination protocol as simply a classical test on an underlying probability density. And so, you know, that's basically the punchline, that we get the other inequality. Like no matter what you do in quantum mechanics, you're going to be limited by a classical test on the underlying probability density. So that leads to that equality, the main theorem, and that's one of our main insights, and it applies to all kinds of functions as well, and it applies for estimation, okay? And so, you know, the talk's done, but the rest of the talk was just like drawing all this, you know, knowledge from classical statistics and decision theory to make statements about like asymptotics of the error probability, and like you can incorporate anything that you know about classical hypothesis testing to apply it to the bosonic dephasing channel. So you can consider asymmetric error setting. I won't go into that in detail. You can invoke like what's known about the error exponent. In the classical setting, you get what's called Chernoff divergence. I was blown away last year when I learned that Hermann Chernoff recently celebrated his 100th birthday. He looked very happy in the picture. So it made me think like, oh, if you prove some remarkable law of large numbers or asymptotic statements, maybe you're so happy that you just live a very long life. And so I hope to you know, do that at some point. I don't know. I just thought that was interesting. Also, Rao of the Kramer-Rao-Brown lived until like 102. That was very interesting. There's probably more examples. Okay, this is a plot. I'll just show you this, and then I'll go to the conclusion slide, because it might be nice to see an example. So there are very lovely Wikipedia pages about what's called circular distributions, and there's in fact whole books. So what does that mean? If you take a normal distribution, that's on the real line, right? But here we're talking about phases. And so if you take that distribution and then wrap it around the unit circle, you get what's called the circular distribution, right? And so when you do this for the normal distribution, it becomes wrapped normal. And that might sound maybe contrived, but actually there are very natural physics models for the bosonic dephasing channel that lead to the wrapped normal. And in fact, it's what I would call like the canonical bosonic dephasing channel. Okay, so you can compare, you can look at the symmetric error exponents. Let's suppose that the first channel has a fixed variance. Yes?
The circle group is the character group of the real line.
Mm-hmm.
So that's where you get that.
Yes.
So it's natural when you wrap it around.
I see. So you're arguing that it's not contrived, in fact, it's quite natural.
That's right.
Yeah.
Sorry.
Yes. Okay, so with this wrapped normal example, what you find is that if the first channel, we set its variance equal to 1, and then we look at the error exponent as a function of the variance of the other channel, then if the variance of the other one is small, then they're highly distinguishable, and the exponent is large. Remember, the exponent is the negative log of the error probability, and so you want that to be large for a small error. And then as the variance approaches 1, the first one selected had variance 1, and so they're indistinguishable. The Chernoff exponent is 0, and then it slowly becomes more distinguishable but kind of tapers off. So let me stop there. I had other things about estimation, and also I felt bad. The title is communication. I didn't talk about that at all, but we have results there, and I have a whole like separate talk about communication over bosonic dephasing channel. I'm going to be here tomorrow, today and tomorrow, and so if you're interested, I can go through some of that with you. So, conclusion. The basic message was that we have these exact solutions, and it's a consequence of a reduction from quantum to classical for these channels. They were somehow simple enough that we could do this. This kind of thing is rare in quantum information, but it's also, we view it as really nice because these bosonic dephasing channels are very interesting from a physical and practical perspective. Okay. As I mentioned throughout, the main open question is to extend all these results to the finite energy case. We have a number of ideas that we're working on. So, thank you.